This is a Kenwood TR-7400A 2-meter FM transceiver. This came out, I think it was 1977, so it's been around a long time. I acquired this from a hamfest recently. According to the guy I bought it from, the power's low and it sticks in transmit in the high power mode. And this thing is rated for 25 watts on high power and 5 watts on low. The receiver, it's a dual conversion receiver, 10.7 and 455 kC IF standard. So I don't know, I just hooked it up to power, so let's power it up and see how it goes here. Okay, 146.5. I have a handy talkie, my trusty HTX 202 on 146.5. I'm going to transmit. Test 1, 2, test. Hello, test. Receiver seems to work. Okay, let's try the transmitter. Test 1, 2, test 1, 2, test. Hello, test. You can see on the watt meter over here, we're getting output 1, 2, 3 test. I'm going to go to high power now, and we'll transmit. And testing 1, 2, 3. 1, 2. We're still getting audio through the transmitter, but the transmitter is locked in transmit mode. And I went back to low power, and it's still locked up. So let's try this. We'll turn it off again. Power it on. Works okay. High power. Locks up. Okay, we're still getting the audio 1, 2, 3 test through the transmitter. Okay. This might be a minor problem, hopefully. So obviously I don't think it's got any major problems. So I'm going to open it up and we'll go through the schematic. Maybe we can find out why this thing is locking up on high power. So that will be the next step. Here is a look at the layout of the Kenwood TR-7400A. This is the top of the unit. The speaker's under here, of course. I removed the screws. And here's the input here. And if you look here, this is the front of the unit. On this end here, you've got, you can see, here's a display unit here. Each of these little segments plug in, which is kind of interesting here. This is one of the earlier synthesized units here, so the phase lock loop is made up of discrete components, so it's a little bigger than some of the newer units here. On top here you see the phase detector section here, which is above the VCO underneath. This section here is the transmitter unit. Here you see the transmit relay. In the back here is the PA under here. You've got your adjustments for tuning here. There's a 5-volt regulator here. Looking on the back, you have your switches that are connected to this board here, and that's cable back into the unit. Here you find the VCO section here. This is the receiver section. It's got 3 helical resonators here, which is nice on the input here. And then you've got your PA amplifiers are connected to this heat sink here to dissipate the heat. Here's your input antenna connector. The power comes in here. I like the layout of these boards. They're really nice. Japanese do really good workmanship. I love these early Japanese radios here. This one has the tone board here for CTCSS, but unfortunately this is 131.8. So that is not what we use in my area here. We use 123.0 on most of the repeaters, but I think what I can do, I have a ComSpec tone board. I might be able to fit in here someplace. I'll have to see. Anyway, that's the layout of the board here, so we'll move on to the next section. Well, this may be a clue. I've got it set at 146.5 on low power. I'll key it. That's going up to 15 watts. On low power, that shouldn't be set that high. But here's what's interesting. Now I'm going to set it to 147.9. Now in the instructions, it says to adjust the low power for 9 watts at 147.9. So I'm going to key it. Now watch what happens. It's still on low power. I key it. 15 watts, but it's stuck. It's stuck in the transmit position. So now I have to power off. I can power it back on. I'm going to go back to 146. Go back to 146.5, low power. Now, what's interesting is on the schematic here, they say to adjust VR5, which is here, in low power, so the unit outputs 9 watts. But I'm getting almost 15, so I can't believe that this is the problem, but I'm going to try it anyway. I'm going to try to adjust VR5 in low power and see if I can see if that solves the lockup and transmit. I'm not sure if that's it, but we'll try it and see, so stand by for that. About 9 watts. Test 1, 2, test. I'm going to go to high power. And it's still locked up here, about 25 watts. Test. But one thing I've noticed, when I key it, it goes up just a little bit when I key it. Just about 25, and then it drops back down. So that's interesting. I guess that's a clue. Okay, I went back to low power. Test 1, 2, and it didn't lock up. Test 1, 2, test. Alright, well, anyway, time to move forward here. Next step. This is really interesting. I have a voltmeter across the transmit relay. Now when I transmit in low power, volts, 12.6 volts, and then it drops slowly. But now when I go to high power, I'll hit transmit, goes up to 11, not quite up to 12, and I let go, and it just drops to 7. It doesn't drop back down. Now I'm going to hit low power again. So that's interesting. Now if you look on the schematic here, that relay is connected to the plus 13 volts that come in through the power switch. It's connected on this side. The other side, to trigger this, if you look over here, on the mic switch, pin 2, when you close that switch, in other words you connect pin 2 to 4, you basically ground this green line. And that green line is this side here. So push to talk grounds this point here. And when I let up, I remove the ground. On high power, that is still staying high. The only other place that feeds that relay, if you look up here, is on the PA board. The antenna input that comes into this device here, which would be here, if you look here, comes through this connector up to this point here. Now, when you want to transmit, TXB goes high, plus 13 volts. That forward biases D3 and D2, and what that does, it allows conduction of the transmitter through this output network into the antenna. But it also forward biases D2, which effectively shorts out the receiver to protect the receiver. And then during receive, TXB drops down to 0, and at that point these two diodes are not biased on, so the receive coming in can come in through here and coupled into the receiver. Anyway, that's how they use pin diodes to control between transmit and receive, where the RF is either coming or going. The TR relay is removed. I'm measuring from the left side of the relay, which is the ground side, to ground with an ohm meter, and when I key it, it drops down to 1 ohm, which is pretty close, allowing for the wire. So the problem isn't in the mic grounding it, that's working. I don't believe this. Here's a suppression diode across the relay, which I, thought, well, yeah, you gotta have that. But look at what's underneath. Here's a diode. Here's a wire, which I don't know where that's going. There's another diode underneath there hanging in midair. So figure that out. I'm going to remove all of those and replace the diode that's there. It looks like a real old diode. I'll put like a 4007. Okay, this is running over there, so I'll have to be careful. Yeah, these two, see if I get it in frame here. Yeah, this wire's running through there. It looks like there's been some heat on here. Somebody's heated up some of these connections. Yeah, I'll have to, and look at this, has been overheated on this side here. So I'm going to perform that, and then we'll see if we get lucky. Stand by for that. I replaced the suppression diode across the relay, and I removed, actually there were 3 other diodes, 2 hanging in space, so I don't know what that was about. So I put a 4007 across the coil, and she still latches up. So low power okay, about 9 watts. High power latches up. It doesn't matter what frequency it latches up on all high power ranges, so we'll have to dig a little deeper here. I'm going to check the alignment on the transmitter here in case either things have drifted out of tolerance or maybe they were helped along the way. But anyway, I'm going to start here. I need to adjust this coil for 10.7 megahertz at a certain test point 1 here, so I see that's off a little bit. So I'm going to adjust that up. That should be 10.7 plus or minus 200 cycles, and that looks there, 10.7. That would be L3 on the transmit board here. Well, I had a hunch. A couple of these adjustments here looked like they had been tampered with, and I didn't find any components that looked out of order, so I did an actual alignment, and I'm glad I did, because that was what the problem was. The transmit here was pretty much screwed up. Anyway, that was the problem. I've got the service manual here, I went through the adjustment procedure. It was pretty simple. Used my RF voltmeter and my trusty, my 485. I love that scope. Sorry, Siglant. Got the service manual here, and I just follow through. This is available on the internet if you want to download it. Anyway, going through the complete alignment of the exciter and the PA unit, setting the protection circuit here, pretty much on these 2 pages here, 37 and 38 of the service manual. That problem went away, so I'm not sure. The only thing I can think of is there's some kind of a feedback from the RF that got into the thing that caused that relay to stay stuck in high power. Like I say, it didn't happen in low power, it was just high power. Plus the power was way off. It was way out of adjustment. I had to adjust pretty much all of the outputs here through the PA to get the thing to get maximum output, so it was fairly low. Anyway, the unit's working now. To use this on local repeaters, I'm going to have to come up with a different arrangement for a tone encoder. Like I say, this one is set for 131.8 cycles for CTCSS, so I'm going to look for a ComSpec encoder board that I can set with dip switches. If I can fit it in here, which I think I can, I will do that. At 146 megahertz, we got about 0.17 microvolts for 12 dB sinad, so that sounds good enough for me. I just found this in my junk box, a communication specialist tone encoder. And this is the SS-32. And so I've got it hooked up, red to positive, black to negative, and the output hooked up to a scope, and it's working 123.0, and I can vary the output with the pot here. Oops, never say oops. You can see. Anyway, the question is, I need to find a place I can get this in the transceiver without interfering with something on board the rig, so that will be the task next. Yeah, you can program these with dip switches for any of the tones. Here's the switch programming for that. And here is a pictorial of the board. So I was lucky to find information on that thing. I took this out of a, believe it or not, an old Motorola handy-talkie that I scrapped. So I'm glad I did. Anyway, let's see if we can find a place in that Kenwood to hook this up, and then the white cord here will be the tone, and then I'll switch the positive lead with transmit. So this will encode only. Transmit and code. I've connected the PL encoder board into the unit here. Excuse the flying leads. Here's where I connected it up here. I picked up a ground on pin 1 on this terminal here. The 2 inside ones are ground. The positive voltage for it I picked up off of a TSB1. When you activate for CTCSS via the switch on the front of the radio, this point goes positive. So I'm tapping off of that on this point here. And then the input here, I'm connecting to pin 1 here, which goes directly down and feeds in at this point here where the normal tone comes in. And that would be through C78. Here it's an electrolytic cap. So I'll demonstrate it. I have it hooked up on a monitor. Right now I have a handy talkie here that's on 146.0, and I'm going to transmit, and you see the receive light comes on, but you're not getting any audio because I'm not transmitting a PL tone. So now I'll turn the switch on the front of the radio to activate PL, and there, testing 1 2 3 test. You can see, once again I'll turn off the PL. Green light comes on, it's picking up the signal, but it's not opening the squelch. So I think this is going to work. Let's see. What I have to do is find a place to put this in here. It would fit over this point. Unfortunately, that's on top of the VCO, and I'm not sure I want to do that. There's enough room, but it might cause a problem unless I make a shielded and have a piece of mylar and insulate it. There isn't a lot of room in here to put this in here. So the next step will be to find a place to mount this inside the radio. But at least I know it works. And you can set the level with this pot with a yellow control on it here. Set it for a deviation of I think 400 Hertz, something like that. A little more maybe, whatever. Some of the repeaters take a little bit more to open. I've accessed a few local repeaters and it seems to work okay. So that will be the next step. And then I'm going to put the hatches back on and put it on the air and see what we can do. There weren't a lot of options of where to put this tone board, so what I didn't want to put it over the VCO, but that's about the only open spot I had here that it would fit. So I've embedded it in a mylar sheet here, and if I need to change it, I just pull it out of this mylar tube and I can change the dip switch. But I don't foresee doing that, and the lid will fit on here too, and it does work. Here's no tone, and you can see it's not opening. Here's with tone. Test 1 2, test 1 2. So it is working. Anyway, I'm going to put it on the service monitor to make sure I haven't done any harm to the VCO here, but it seems to work okay. So anyway, that's it for the tone board. Units back together and seems to work alright. Test 1 2, test 1 2, test. Hello. 1 2 test. Anyway, that's now I can use this on repeaters here. I like this radio. It's built like a tank. I'm going to give a brief description of the PLL in this. This is interesting because this was in the late 70s, and prior to this, most VHF transceivers, you needed a crystal for the transmit and receive whatever you wanted to transmit on. And then the invention of the modern phase lock loop allowed them to generate pretty much any frequency range in the band that you wanted, in this case 2 meters. So I'm going to do a brief description of the phase lock loop. This is all done with discrete components. Of course, nowadays and later on, they came out with chips that basically did it the same thing here. So this is a schematic diagram of the VCO. And the way this operates is, on this section here, Q7 is a Colpitts oscillator. You can see the 2 caps here. And its frequency is controlled and varied by a varactor diode D1 here. And that gets a control voltage in through CV, control voltage line. The DC coming in from the phase detector will vary the capacitance of this diode, and that varies the frequency of Q7. The output of Q7 is coupled to Q6. This acts as a buffer which amplifies that and isolates the oscillator, and then that's connected down to gate 1 of Q12. This is the amplifier that amplifies the signal that's applied to the transmit and receive mixers. So the output of Q12 goes through D6 to the receive mixer, and it's coupled through D7 to the transmit mixer. Q8 over here is a crystal oscillator, and it'll generate one of two frequencies. Either if you look here, if D2 is turned on by a DC voltage here, which forward biases D2, then this crystal, which says 42.645 megahertz, controls this oscillator. And if D3 is turned on by a DC level here, then 42.643, let's see, what's 42.6433 megahertz is generated by Q8 here. The output of that oscillator is tripled in Q9, and its output is here through L11. So basically the output of this is 127.9299 with D3 energized, or D3 forward biased, or 127.935 with D2 forward biased. And then that output is connected up to the mixer Q4. Through the mixing axis of Q4, this produces 5.37 to 9.36 megahertz. Goes through a pi filter and then amplifier buffer Q1, 2, and 3 here, and then that output is connected through P1 to the phase detector. Down here, Q13, this is just a switch that turns this amplifier on and off. If you lose lock of the VCO, this transistor will turn off Q12, and it'll inhibit you from transmitting any out-of-band signals. So it's basically a safety device if you lose your VCO lock. Now turning to the phase detector, which is this circuit. Okay, the output from the VCO is connected to P1 here, and that's connected to Q6, and that buffers that 5.37 to 9.36 megahertz output, and that is amplified and it's applied to IC8. Now these quad input, 2-input NAND gate, they're connected as inverters here. The whole purpose of this section here is to divide the signal down, resulting in a 10 kilohertz output that's fed to the phase comparator. So basically IC5 through IC12 here, they're controlled by rotary switches on the front of the transceiver, and they control the divide by N number for the phase detector here. And then the output's applied here, and then the VCO will change frequency to keep that reference at 10 kilohertz. Now you need a reference oscillator for the phase lock loop, and that's produced in IC1 here. Here you see a crystal 5.12 megahertz, and that is applied to this IC, which is connected as an oscillator, and also internally this is divided by 2, and it's connected to IC2, which has a division ratio of 16, and IC3, which also has a division ratio of 16, and that's applied down to the phase detector IC4. So that reference level is crystal controlled, and it's 10 kilohertz. And that's where you get your stability. Because it's crystal controlled and its reference is 10 kilohertz, it will compare the 10 kilohertz that's output from the division here, and if that isn't 10 kilohertz, that'll produce a voltage that will pull the oscillator, the VCO oscillator, so that the output of this divider is 10 kilohertz. Now the phase detector, it has a charge pump, and that output is on pins 5 and 10 here. They're used to control the output of the VCO, and here you can see they're connected through, there's a big cap here, it's 22 microfarads that filters it, and then it's applied to a series of 3 amplifiers here, which provide isolation and amplification, and then they're applied to CV. This is the control voltage for the VCO, and if you look back up here, that's the control voltage that varies the frequency of the VCO. So what happens is this voltage on CV will vary, and it will vary the frequency of the VCO to always keep it in step with the reference oscillator down here. So if that VCO tried to drift off frequency, the phase detector in IC4 would detect that, and it produce a correction voltage which should go back up to the VCO and pull it back on frequency. That's where you get your stability. The VCO is referenced to a crystal oscillator, the reference frequency down here. Now if the VCO becomes unlocked for some reason, D1 or D2 will turn on Q5, and that will turn on Q4, and that's connected up here through LE, and that's connected back up to the VCO at this point. It's not marked, but this is LE here. So that will basically ground that terminal, and that turns Q13 off, and that'll turn off Q12, the amplifier, so you lose your signal for your 2 mixers, your transmit and your receive mixer here. So that protects so you don't transmit any spurious signals that'll get you in trouble. Well, anyway, that's how this works. I just thought it's really interesting how they did it back in 1977. Of course, after that, a lot of really neat integrated circuits were invented that did all these functions on a single integrated circuit. You know, you just add a couple little devices to that to do that, but took up a lot of real estate in the transceiver. Well, that'll finish this video for the Kenwood TR-7400A. Normally the rule is you can't align a radio to fix it, but this thing was so far out of alignment that appears to what caused the trouble here, why that thing would hang up on high power. I really can't tell you why that happened. Obviously something was keeping the transmitter keyed with that much energy and high power, so I did a complete transmitter alignment and the rig is working good. So that'll do it for this one. Thanks for watching, and we'll see you in the next one. Bye for now.